In this module, I'm going to talk about the different Markov chain Monte Carlo diagnostic methods, to know about the convergence, to know about the minimum sample required, the minimum burn-in requirement, and different diagnostic procedures that exist in MCMC literature. So I'll also show you different graphical methods, to assess whether the samples are coming independently, whether the chain is reached to the stationary distribution or not. The autocorrelation plot, the time series plot, these few plots that I will show you, how those plots can be used to interpret about the convergence of the MCMC chain. Then show you some Dillman test, and then say some tests that might help you to calculate or assess the minimum sample size that is required to generate before you reach the convergence, reach the stationary distribution of the Markov chain. In this module, we are going to see the different metropolis testings, or rather MCMC diagnostics procedures that are there, and especially focus on the convergence of the metropolis testing sampling. So let's define a function that does the random walk metropolis testing sampling when supplied with the required arguments such as target density, starting point of random walk, the variance covariance matrix for the multivariate normal that is used as the proposal distribution for random walk metropolis testings, and burn-in length for the chain. So these are the few arguments that will pass through a function, and then the function will generate a multivariate random walk proposal. So here I'm just defining this through the my WR metro function is a target n, then comma x, then variance covariance matrix, then burn-in, and by default I'm setting as 0 burn-in, and the required package is mass, then my samples equals to x, then I'm using a for loop, and then here I'm just putting the burn-in arguments. Is that the 2, it will start from 2 to burn-in plus n. So if you put the burn-in, then it will take if 1000 is required and burn-in is 500, the total sample will be generated around 1500, the one less 1500 as per the for loop. So that then the proposal L is actually here for the random walk. I'm assuming the multivariate normal for n equals to 1, and the x is the x, and variance covariance matrix is VCOV that has been already is another argument. And now here is the metropolis algorithm that I am putting. If the random R unif 1 is less than minimum of 1, and the ratio of target L by target x, and x is the prop L, otherwise it is the initial value itself. So it is a previous state, and my sample should be stored in the sample should be stored in my samples, that is R by in my samples comma x, and my sample is actually now here I'm just excluding the first burn-in number of samples as burn in plus 1 to n plus burn-in. So it will discard the initial few samples as per your requirement. If you say 500, then it will exclude first 500 samples from the return value. Then we'll define an arbitrary bivariate function. So I define a multivariate metropolis random walk metropolis sampler, and now I'm using one function, it's arbitrary function, say f xy equals to e to the power minus 5x square y square minus 1, just for demonstration. This looks like a ring radius of radius 1 and xy from the xy plane and centered at the origin. So first we'll draw a plot that the actual curve of that particular function So let's define a function that carved 3D that I am defining, where function would be passed through, then from to x and from to and from y, and from x to x, from y to y, and n equals to how much? Say 101 is the default value, and this is the function. Just go through this function, then it will tell you how I develop a carved 3D function that will help you to draw the 3D curve. In the next slide I will show you. And the function is, say, this fxy function is defined as g equals to function x e to the power x into absolute value x square, x2 square, and x is actually the x1 and x2, that is x and y is combined into x and y, and the single arguments I am keeping, but the single arguments will have two components, x1 and x2, that is x and y as per the function. And if you just draw it from minus 1.5 to 1.5, minus 1.5 to 1.5, and n equals to say 100, that will give you this 3D plot. So this is the bivariate function of the arbitrary equation that I assume. And now let's apply the Metropolis-Hastings, the random walk Metropolis-Hastings algorithm to generate the sample from this density, this function. Here is the example. Say variance covariance matrix is of 2D is 0.1 into diagonal of 2, and then R sample equals to my RW metro, and then the function G is the target function, then 50,000 sample, initial values are 0 and 0 initial, and then variance covariance matrix is the V curve 2D, and that will give you the sample. And if you plot if you just plot it through plot function, you will see it is quite similar like the previous plot that we have seen. Now let's focus on the MCMC convergence. Just for demonstrating this convergence methods, I developed that multivariate random walk sampler and use one example to demonstrate it. Now, from the theory of Markov chain, we expect the chains to eventually converge to a stationary distribution, which is also our target distribution. However, there is no guarantee that our chain has converged after m draws. The question is then, how do we know whether the chain has actually converged? We can never be sure, but there are several tests we can do, both visual and statistical, to see if the chain appears to be converged. For all convergence diagnostics, we are going to use here from a CODA function, a CODA package in R. Before we use the diagnostics, we should turn our chain into a MCMC objects. We can tell the MCMC function to burn in and draws with the start and end arguments. So MCMC also has a thin arguments which only tells it the thinning interval that was used. So here the R sample that I have generated, the multivariate random walk metropolis, that should be passed through MCMC. Then it will convert into a MCMC object. So now say mh.draw equals to MCMC R sample. So now our sample become the MCMC object by mh.draws variable. Now we can see the summary of MH draws. Just write summary and pass the MH.draws object. It will give you the summary of the sample that you have, the mean of two variables that you generated, the standard deviation, the name estimate, the standard error, time series standard error, etc. The results gives the means, standard deviations, quantiles, each components of random variate. The name standard error is the standard error of mean, which capture the simulation error of the mean rather than uncertainty. The time series standard error adjusts the naive standard error for autocorrelation. visual inspection, one way to see if our chain has converged is to see how well our chain is mixing or moving around the parameter space. If our chain is taking a long time to move around the parameter space, then it will take longer to converge. We can see how well our chain is mixing through visual inspection. We need to do the inspection for every parameter. A trace plot is a plot of iteration number against the value of the draw of the parameter at each iteration. We can see whether our chain gets stuck in certain areas of the parameter space, which indicates bad mixing. So here is a plot. If you just plot image draws, then you will see this plots. It's looks like it's smooth. Suppose in this area it seems little bit it's stuck. That means this is some indication, little indications that the chain is getting stuck here. This is called bad mixing. When it's coming random ups and downs, then it is a good mixing. So this curve will tell you whether any bad mixing is there. Suppose if this flat position is very long, then definitely it got stuck here. Similarly, you can see the autocorrelation plot of image, these things that also will tell you whether the independent samples are coming or not. That and whether how fast the autocorrelation dying down from this autocorrelation plot. The rejection rate of MH algorithm, we can also get a rejection rate for Metropolis-Hastings algorithm using rejection rate function. To get the acceptance rate, we just want 1 minus rejection rate. That's quite simple. Say rejection rate function, so remember R is the uppercase, so rejection R rate, then image dot draws if you give, then variable 1 and variable 2. So rejection rate is 29% and almost 30%. So acceptance rate is almost 70%. So now we'll see the Dillman-Rubin multiple sequence diagnostics. So Dillman-Rubin diagnostics, say I'm just stating the different steps for this diagnostic process. For run m greater than 2 chains of length to 2n from over dispersed starting values. Discard the first n draws in each chain. Calculate the within chain and between chain variance. Calculate the estimated variance of the parameter as a weighted sum of within chain and between chain variance. Calculate the potential scale reduction factor. The interpretation is, if we have more than one parameter, then we need to calculate the potential scale reduction factor for each parameter. And we should run our chain out long enough to show that all potential scale reduction factors are small enough, perhaps less than 1.1 or 1.2. We can then combine the m into n total draws from our chains to produce one chain from the stationary distribution. See, the first we run m chains at different starting values, say m equals to 5 here, and convert them to a MCMC objects. And we then put m chains together into a MCMC list and then run the diagnostics with Dillman.diag function. So first I'm drawing 5 different chains. Say MH draws 1 is the same function that bivariate random walk sampler, Metropolis sampler that I developed, and the 5,000 size samples that I drawn here, image draws 1, 2, 3, 4 and 5, and then put all into a MC.list, then list of image draws 1, 2, 3, 4, 5, and then that list has to be passed through a Dillman.diag function. say Gellman.diag, then image.list, then you will see the potential scale reduction factor. The point estimate is 1.01, 1.24. The upper confidence limit is 1.02 to 1.64. So 1.01 quite fair. The multivariate PS RF is 1. Scale reduction factor is 1.28. And somehow it's still acceptable. We can see how the potential scale reduction factor changes through iteration using a Dillman plot. So we can change the scale reduction factor and we can change the number of iterations and see how it is reducing or how it is functioning. The potential scale reduction function. For that you can use Gellman.plot, and that image list object has to be passed through Gellman.plot. If you pass through Gellman.plot, you will get two plots for, because you have a two variable bivariate function that we have generated. So it will give you two variable. One is the median and another is the 97.5%. I mean, that is, one is the average one, another is the 97 point, that is the upper confidence limit. So it is the upper confidence limit. So the dotted lines actually the upper confidence, and the dark color line is actually the median, and in the x-axis is the last iteration in chain. So iteration number increasing, and we can see that the shrinking factor is gradually decreasing, the scale reduction factor gradually decreasing. So we can actually identify where, seeing this plot, we can easily identify wherever you can see that the scale reduction factor is going down to 1.2 or 1.1. So you can set your sample size there. So that would be your chain size that you need to generate. Another diagnostic methods then we'll see is the GeoX Diagnostics methods. So can we treat, say, the first 10,000 iteration as burn-in? So how do you get this answer? How much we need to burn? This GeoX diagnostic method might give you some idea about how much burn-in required. In a long enough chain whose stress plot suggests the convergence to the target distribution, we assume that the second half of the chain has converged to the target distribution, and we test if the first 10% can be treated as burn-in. The idea is mimic the sample a simple two sample test of means. If the mean of the first 10% is not significantly different from last 50%, then we conclude the target distribution converges somewhere in the first 10% of the chain. Then GeoX Diagnostics use a spectral density to estimate the sample variance. Originally, the bivariate GeoX Diagnostics, GeoX Diagnostics was only designed for univariate scenario. One way to expand it to a bivariate scenario is to also consider the sample covariance between the two variables x and y. Suppose a bivariate chain x and y is considered. After performing GeoX Diagnostics for each chain, calculate this expression gamma I equals to xi minus x bar into yi minus y bar for each draws of x and y. Then perform the GeoX diagnostic for the sample of the burn-in for the sample, and burn-in is chosen as the early proportion that passes all the three diagnostics. So here is one example of say image from gamma distribution. So this function is developed just for drawing gamma variate by image metabolic Hastings random walk sampler. So this is a random metabolic Hastings random walk gamma sampler that have been defined here. Now I am using a library CODA, then set seed is 100, then object equals to image.gamma, then it will give you the gamma samples, and then this object is actually the gamma sample where I specified it is 10,000. And now what I'll do, that the GeoX.diag diagnostic is a function that we can use from CODA package, and then of course that object, that the sample that we have generated has to be converted into MCMC object. So we'll pass to MCMC object that sampler and that sample to get the MCMC object. That MCMC object would be passed within the GeoX diagnostic function, and then type GD. The GD will give you the details about this. So it is variable 0.57, and the test the p-value is telling is 0.56, two-sided variable 1. And then we also can do a bivariate normal Gibbs sampler. This you can define this function. Bivariate normal Gibbs sampler is this, and then set seed equals to 100, object equals to Gibbs dot binorm. Just look into the functions, how it is defined. I think hopefully it would be easy for you to understand how the bivariate normal Gibbs sampler has been defined. And then object is the Gibbs dot burn, and that convert that object into MCMC object and pass through the GeoX diagnostics, and that will give you the p-value. This p-value for y is actually this. Then p-value for sample covariance you can calculate by gamma by this formula, and then you will get the for the bivariate one, for the third component that we had, gamma I that we defined earlier, for that p-value is 0.19. Suppose the other one, another diagnostic methods is the Raftery and Lewis diagnostic. So the suppose we want to measure some posterior quantity of interest Q. If we define some acceptable tolerance R for Q and the probability S of being within that tolerance, the Raftery and Lewis diagnostics will calculate number of iteration N and the number of burn in M necessary to satisfy the specified condition. The diagnostics was designed to test the number of iterations and the burn-in needed by first running the test, running and testing shorter pilot chain. In practice, we can also just test our normal chain to see if it satisfies the results that the diagnostic suggests. The input are: select a posterior quantile of interest, say Q, for example, say 0.025 quantile. Select an acceptable tolerance R for this quantile. For example, if R equals to 0.005, then that means we want to measure the 0.025 quantile with an accuracy of plus minus 0.005. Select a probability S, which is the desired probability of being within Q minus R to Q plus R. Run a pilot sampler to generate a Markov chain of minimum length given by rounding of n min is this expression. So this expression will give the minimum length that you need. So now where phi inverse is the inverse of the normal CDF. So that is the Raftery Lewis diagnostics, RL diagnostics. We can again, that image draws that objects that the first random walk multivariate random walk sampler that I have generated, that is image draws that MCMC object can be passed through Raftery.diagnostic function, that is Raftery.diag. Remember, these all functions are from CODA package. So you have to load the CODA package first and then specify the quantile Q equals to 0.25 and then R equals to 0.005 and S equals to 0.95. The quantile Q is 0.025, accuracy is plus minus 0.05, the probability equals to 0.95. Then here is the required N n required n is this, n lower bound minimum is this, and the dependence factor is 20.4. I and dependent these things, I mean the interpretations are below actually. M is the number of burn-ins necessary, n is the number of iteration necessary in the Markov chain, n minimum is the minimum number of iteration for the pilot sampler, and I the dependence factor interpreted as the proportional increase in the number of iteration attributed to the serial dependence. High dependence factor greater than 5 are orisome and maybe due to the influential starting values. So high correlation between coefficients or poor mixing, I mean that could be the reason for the high dependence factor but more than 5. So some notes, the Raftery-Lewis or RL diagnostics will differ depending on which quantile Q you choose. Estimates tend to be conservative in that it will suggest more iteration than necessary. So it only tests the marginal convergence on each parameter. Nevertheless, it often works well with simple models. The last diagnostic methods that we are going to learn today is the Hindenburg Welch diagnostics, that HW diagnostics. The HW diagnostics calculates a test statistics based on Kramer-von Mises test statistics to accept or reject the null hypothesis that Markov chain is from a stationary distribution. So this will test whether it is converging to a stationary distribution or not. So the diagnostic consists of two parts. The part 1 is generate a chain of n iteration and define an alpha level, calculate the test statistics on whole chain, accept or reject null hypothesis that the chain is from a stationary distribution. If the null hypothesis is rejected, discard the first 10% of the chain, calculate the test statistics and accept or reject null. If null hypothesis is rejected, discard the next 10% and calculate the test statistics. Repeat until null hypothesis is accepted or 50% of the chain is discarded. If test is still rejected, null hypothesis, then chain fails the test and need to be run longer. The second part of the HW diagnostics is if the chain passes the first part of the diagnostics, then it takes the part of the chain not discarded from the first part to test the second part. The half width test calculates the width of 1 minus alpha % credible interval around the mean. If the ratio of the half width and the mean is lower than some epsilon, then the chain passes the test. Otherwise, the chain must be run out longer. So here is the Hildel diag. This MH dot draws that object I can pass through, and that will give you the test p-value. The p-value is 0.407, 0.57. So it is actually, it's showing it is accepted, and variable the half mean and half width is actually failed. So I mean these are the few MCMC diagnostics should be run before you use the MCMC samples to check whether it reaches stationarity or it's converging there, and it also help you to assess how much sample size is required, how much burn-in is required to get the independent sample or the sample from a stationary distribution. In this module we have learned the different diagnostic methods for MCMC convergence. So we saw how to assess the convergence through graphically. We saw how to do some statistical tests to assess whether convergence reach or not, that is the distribution of the chain reach to the stationary distribution or not, and how to get an idea about the minimum sample size required before the chain reach to the stationarity, how much burn-in required before reach to the stationary distributions or before the Markov chain converge.